Welcome to my video, Electrical Power and Energy in Circuits. First of all, what is electrical power? Electrical power is the rate at which electrical energy is converted into another form of energy, light, heat, motion, etc. So our formula here is the power is equal to the voltage times the current in a circuit, or P is equal to V times I. And the power comes in units of watts, and the voltage in units of volts, and the current is in units of amperes. And we've seen this before in the Ohm's law video. So the key idea here is a device that draws more current or operates at higher voltage will use more power, right? As V and I get bigger, the power gets bigger. Now if we combine Ohm's law with this, V is equal to I times R, then we can change the form of it. The power, this is our basic form we had earlier, V is equal to, power is equal to V times I. And then if we substitute Ohm's law into that, either solving for V or solving for I, what we're going to get is the power is equal to I squared times R. That's if we know the current and the resistance. And the power is equal to V squared divided by R if we know the voltage and the resistance. It depends on what we're given in the situation. And these formulas also apply to DC circuits, which are direct current, like in a battery, or AC, alternating current, which would be like in your house. But if you get into the details on the AC, you get into such things as RMS voltage and power factor, and it gets a little more complicated. As a general rule, these work in most basic cases. Now, electrical energy is the total work done by the circuit over time. So related quantity to power is electrical energy. So the energy is equal to power times time. How long are you using this? How long are you running a light bulb, running a motor? Whatever requires electrical power. And then however long you run it takes the energy. So the energy is equal to power times time. The energies are units of joules or in kilowatts or kilowatt hours. Kilowatt hours would be typically what you would use for home-related measurements. Power is measured in watts, and then the time is measured in seconds. And so for household electricity, which is alternating current, energy is usually measured in kilowatt hours, and 1 kilowatt hour is equal to 1,000 watts in 1 hour. Let's look at an example. Power in a resistor. A 12-volt battery is connected to a 6-ohm resistor. So here's our 12-volt battery. It's connected to a 6-ohm resistor. And the current through the resistor and the power dissipated. That's what we want to know. What's the current and what's the power dissipated by the resistor? So the current we know from Ohm's law is voltage divided by resistance, 12 divided by 6. So we've got 2 amps flowing in the circuit. Now the power consumed by the resistor, since the wire is assumed to be a perfect conductor, it doesn't dissipate power. It's not totally true, but it's a good approximation. Power is equal to voltage times current, 12 volts times 2 amps, is equal to 24 watts. So the resistor uses 24 watts of power. That's where the power of the battery is transferred, is to the resistor. Let's look at the example of energy consumption. A light bulb rated at 60 watts operates for 3 hours. How much energy does it use in kilowatt hours? So here's our light bulb. We're going to run it for 3 hours. It's a 60-watt bulb. So we convert 60 watts to kilowatts, and so 60 divided by 1,000 gives us a kilowatt because the ratio is 1,000 watts is equal to 1 kilowatt, so it's 0.06 kilowatts. So the energy now is the power times the time, so it's 0.06 kilowatts times 3 hours. That gives us 0.18 kilowatt hours. So the bulb uses 0.18 kilowatt hours of energy. Next example is power within a resistor. So we've got a resistor of 4 ohms, and we know that it's going to be 3 amps of currents going through this resistor. And so find the power dissipated in the resistor. So the power is equal to I squared times R. It's one of our equations that we looked at earlier, depending on we know the current and the resistance. So the power is 3 amps, quantity squared, times 4 ohms. That's 9 times 4, that's equal to 36 watts. So the resistor dissipates 36 watts of power. So some of our key points we want to get out of this video is power tells us how fast energy is being converted. Energy tells you how much total work is done over time. And the three power equations allow you to solve for any situation using Ohm's law, depending on what quantities you do know and what quantities you don't know. Energy in kilowatt hours is what utilities use in billing. So that's what you would see in your household bill. Hope you got something out of this and learned a little bit about energy and power and electric circuits. If you did, give me a like, thumbs up, subscribe to my channel. I do want to thank you for watching.